Hello, and thank you for joining today's webinar, Make 3D Printing Work for You, hosted by Material Connection. My name is Caroline Berna, Account Manager at Material Connection, and I will be your moderator today. Throughout our presentation, we encourage you to interact with our presenter by typing in questions using the questions pane. We will answer them live both during the event and following the presentation. If you'd like to join the conversation on Twitter, be sure to follow us. Our handle is @MaterialCX, and use the hashtag MCX3D in your tweets. We'd love to have you connect with us and keep the conversation going beyond today's event. We're also recording this webinar and we'll make the link available following the session. Now on to today's presenter, one of Material Connection's esteemed material scientists, Sarah Hoit. Sarah holds a Master's of Science from North Carolina State University College of Textiles and applies her material knowledge to best serve our clients looking for a material advantage. On behalf of Material Connection's consulting division, ThinkLab, Sarah has worked with a broad range of companies, including Pepsi, Seventh Generation, Avon, Logitech, Tupperware, and SC Johnson. Her material savvy and breadth of knowledge also made her a critical asset in the launch of Material Connection's recent report on additive manufacturing, which is part of the larger Material Revolution Report series, and supported the development of today's webinar content. It is my pleasure to introduce to you today material scientist Sarah Hoit.
Thanks, Caroline. So today we're going to cover a wide range of topics. And don't worry, we are going to cover what is additive manufacturing. But my real hope for the takeaway today is to understand 3D manufacturing, additive manufacturing, and how you can incorporate it into your business. And also why we're doing this talk, as well as why we did the report, is the popularity of additive manufacturing and the volume of information being created around it is an intense deluge. And we're hoping that we can give you today a better foothold or a first foothold to understand the volume of information that's coming your way. So if there's some way to interpret that deluge as it comes your way based on the learnings today, and also to interpret and decide if it is, or in fact is not, a good fit for your business, and if so, how could it be incorporated? Additive manufacturing is going to be a $14 billion business by 2025. We think that sort of number makes it a meritorious topic of conversation in any business. So the first topic we'll cover today, what is additive manufacturing? Different methods of additive manufacturing, understanding the tools and techniques that really build these pieces, who's pushing the boundaries and how it's changing our perception of what additive manufacturing encompasses, where is it headed in the future, and what are the practical ways to adopt this technology? And then, of course, Q&A throughout and at the end of this session. Additive manufacturing in its broadest sense is adding pieces together to create a larger whole. Its opposite clearly is subtractive manufacturing. So if we think about this on a very large scale, bricklaying, right? We're putting together smaller pieces, bricks and bricks and bricks, to create a wall, as opposed to something like stone carving, where we started with a monolithic unit and are carving away the pieces we don't want to reveal the negative underneath. This is also a great point to talk about additive manufacturing as a term as opposed to 3D printing. I like to use additive manufacturing because it's a broader umbrella term and encompasses 3D printing. There are additive manufacturing techniques that are not defined as printing, such as 3D knitting and other things like that, but additive manufacturing encompasses all of them, including 3D printing technology. So there are 4 types of additive manufacturing techniques and tools I'd like to talk about, and I chose these 4 because they are very common in usage. They're used in high volume, and they're ones people are familiar with and are also the core of other permutations. So understanding these 4 expands into the many, many different types of printers, different options, and different brand offerings. There are more options and techniques in the report, but we covered just these 4 today. So the first one is direct filament extrusion. This is often referred to as fused deposition modeling or fused filament fabrication, FDM or FFF. This is the type of system you see in the MakerBot, the Cubex, the RepRap. It's a highly commercially available. They're selling them at Home Depot now. And it is a low-cost, really entry-level option for a lot of people. So you can see from the image here, one of the limitations is that there does need to be a filament. Your material does need to be in that spooled filament format, and also it needs to be a thermoplastic material, meaning that it will melt when heat is applied and then re-solidify. So as you can see here, we're moving that filament through the heated nozzle and the heated block and depositing layers of plastic again and again. The analogy I always make is that it's like a bag of icing. You're icing a cake, and we're piping those layers of icing, and we're building up that structure. It works really nicely for prototyping. It's easy to have one in a design studio or at home. It can also be made actually to make molds. So if you want to blow mold a bottle or make a part, it can be the mold component if you're looking for something more heavy and industrial. It does need to be a thermoplastic material, and it does need to be available in a filament format. There are two materials I'd like to discuss that I think are really novel and interesting that are applicable to direct filament fabrication. This is a range of nylons from Taulman. The ones you're seeing here in fantastical colors have actually been dyed by the person printing them. So as nylon likes to take up water, these have been dyed with a home writ dye, the kind you can buy at a Kmart or a Walmart or a fabric store. So he's actually dyed the filament before extruding it, creating those strata and the different print layers. Also, nylon has great physical properties, and if well printed, a solid block of printed nylon, such as their 618 or 645, will have the same properties as a monolithic block of nylon. It can be drilled, polished, filed, so you can print, and then if you've got a prototype that needs an extra hole, a different finish, that can actually be mechanically applied. You can do a lot of secondary processing to these nylons. So this is great for functional prototypes and people who are looking for also non-destructive testing. The slight translucency allows you to see that internal printed structure and see what failures may have been without disassembling that part fully. This is a material called lace ceramic. Aside from being very beautiful, you can see the strata of the print layers. It's 100% ceramic. So what's fascinating about this is they've taken the ceramic particles and put them in a plastic matrix, so that, as we discussed earlier, the thermoplastic necessity is met. So we're extruding that plastic with our little ceramic particles inside. We're actually going to kiln that. We're going to burn off the polymer component, sinter that ceramic, and leave you with a 100% ceramic piece. So what you're seeing in this image, there's about 25% shrinkage as you have that burn off, but you are resulting in a 100% ceramic piece that can be glazed, that beautiful blue like you're seeing there, and fired and treated like a natural regular ceramic. The next technique is inkjet or powder bed printing. So what you're seeing here is a slightly different configuration, seeing a bed full of powder, and then that inkjet printhead is actually depositing layers of glue. So the analogy I use here is like when you were in kindergarten, you put down glue and you put glitter on top. You put more glue and you put more glitter. So we're layering up. So the pattern in which we're printing is forming the structure of that small toy mannequin inside. What's nice about this system is that we can color the binder. We can color that adhesive or glue. And here you're seeing, so you can get full color prints, which is a really nice option. These do have some challenges. Again, the powder, it does need to be a powder format, which is a requirement which will change your material options. Also, there is self-supporting. The powder around the printed piece will support it, so you don't need to print support structures, which is another benefit. There is the challenge of mechanical stability. You will get a full color piece out, but secondary processing can be limited. And a material that was really interesting in application in powder bed were these sugar. They're sugar cubes and sugar spheres from a company called the Sugar Lab. What I thought was really interesting here is that they've changed the material, but in order to fit the technology, not the format. So you're looking at an edible powdered sugar. They've colored the binder in these fabulous neon colors. And the binder is actually just a water with a flavoring that's dissolving the sugar and binding it together. So when we think about adhesive, we need to think about the adhesive needed for the material as well as a fluid adhesive that's compatible with the technology. Also, what I love about these example, if you look in the lower right corner, you'll see a cube with a sphere inscribed inside. This is a great example of the complexity that can be easily produced with additive manufacturing technologies. In this case, it's a charming novelty. In other cases, this is going to minimize production time, simplify part structure, and also reduce part weight. So if you're working in aerospace, automotive, any weight reduction and part simplification, especially with something with a lot of nuanced pieces, is vital. The next technology is selective laser sintering. Again, this is another powder bed technology, but rather than gluing that powder together, we're going to use a laser to heat, either melt or sinter those pieces together into a larger unit. Again, you get the supportive structure of the powder below. Also, you get very high resolution. The precision you can get with a laser is quite fine. And it also allows for some flexibility depending on the material you're using. This is often done with nylon, which gives you some flexibility and really nice bonding. It can also be done with metals that have a plastic coating around the powdered metal. Boeing has actually been using this technology for about 12 years, and Selective laser sintered over 20,000 parts. So they're capitalizing on the complexity, weight reduction, and fabrication time production lowering that you can get with this technology for their airplanes. Also, we've seen this used some in fashion. If you see some Iris Van Herpen's designs, also that fabulous black articulated dress on Divan tees, those are Selective laser sintered nylons as well. I use the analogy of a creme brulee. You put that powder on top, you've applied the heat, and you've re-solidified that. This is prime part from EOS. Selective laser sintered powder. What's interesting about this one is it's an elastomer. So it's got flexibility. It'll pop back into shape. They've enhanced that through the structure they provided here. But suddenly, rather than looking at prototyping or fabrication that shows us the shape and structure, we can actually have some of the performance characteristics. So if you're producing a shoe sole, you can do that with Inkjet and get a good color representation, a good dimensional stability. But the actual testing of wear patterns or traction wouldn't be possible. With the shift for elastomers and other physical characteristics available with this product, you can start to test that. You can make wearable, functional prototypes. It also opens up, for final products, a degree of complexity in fabrication. The padding and structure you're seeing here is really unique due to that lattice work. And the final one I want to discuss is stereolithography. Stereolithography is an interesting departure from the other ones because rather than depending on adhesive or melting, we're actually going to move from a liquid to a solid. And how that's occurring, you see this liquid bath here in the small chess pieces. As the laser passes through that liquid resin, it's actually bonding the small molecules in the liquid resin together to form solid plastic pieces. So we're moving from free-flowing small molecules and monomers that are being polymerized through the reaction with the light. This can limit material type. The majority of stereolithography materials are acrylics, methacrylates, epoxies. This is also the same technique, a component of it, the UV reactive, that's used in multi-jet and polyjet printing. It's got really high precision, easy clean off, and it offers a level of precision with some support structure and a fine finish on the outside, not offered by very many other options. This material for stereolithography is really interesting. The image you're seeing here, these are metal parts. They're not using a liquid metal in the resin bath. What they're actually doing is they're making the mold piece and then casting the metal. So this is an interesting example. We're using that 3D printer to get fine detail and then creating a mold, burning out the printed component, and then using that classic technique of metal casting based on the high detail we've produced through the 3D printing. So rather than looking at it as a prototyping technique or a final fabrication technique, in this way it's an intermediary that's allowing for new designs within traditional techniques. So as we look through all of those materials and processes, as well as the design, we're seeing how those are intertwined inextricably. Each of those decisions is going to influence another. And if there's one that's non-negotiable, say you own a certain machine, then that will limit the materials and perhaps the design opportunities. Also, the materials that are formatted correctly for a given process will also limit the design attributes. So again, any one of these decisions needs to be made in consort with the other. And this is something actually we think a lot about in ThinkLab, the consulting department, to say you can't make a design and slap some materials on top. We need to think about that very early on in the process to optimize the design for the materials, but then also advance the design through the opportunities materials can offer. There are a whole host of individuals and companies pushing the boundaries of where additive manufacturing is going. They're expanding our perception of what 3D and additive manufacturing are. We're moving outside of the box. So some of those include, again, Dirk van der Kooi. If you look on the left side, this is his custom-developed machine. It's actually a free arm that you've seen probably most often in automotive manufacturing. There's a full range of motion. And then you'll see on the right some of his chairs and tables. So those are full scale. He is printing entire regular sized chairs and tables. What I think is really interesting about this is we've moved outside of that XYZ axis, that box that we envision when we think of 3D printing. And with the freedom of motion, there's more availability for variation in design, as you see with the sort of more squiggly chair in the front. And if you look at the ones in the back, you again see the strata of the build. And I think this calls attention to the beauty of the production, to call attention to the artifacts of fabrication, rather than saying, can I make it look like something produced in a more traditional manner? Can I celebrate the way in which it's fabricated? This machine is called a mini builder. If you were standing next to it, it's probably about, that concrete structure is about waist high. So this can actually move fully outside of any constraints. So like a remote control car, it's running on the track of its previous construction. You'll see in the back there's a tube extruding concrete and some heat guns. It's actually building up layer by layer in a spiral, like you think of a direct filament extrusion, but it's tracking along itself. So whatever outline, whatever dimension we need to set down can be tracked by this builder. So right now they're doing some full-scale sculptures, probably about the size of a small room, but they're hoping to scale up to full buildings. And the last one, this is a Foodini. There are many challenges in printing food, one of which, to be overly obvious, it has to be food. You have to be able to eat it. It can't be a facsimile or a look-alike. It needs to be a consumable good. What I find fascinating, though, is the processing techniques. So if we look at all of these images, they're all extrusion. But in the upper left, we've got a bun. Lower left, some sort of, I think it's a chickpea patty. Upper right, there's a cheese. And lower right is a fully assembled sandwich. What's unique about this is if you can pipe on that dough for the bun, it needs to be baked. Right? In order to make it into food, there are secondary steps. We also need to cook this patty, especially if it's a meat product. So the way in which we're taking ingredients, turning them into processable materials, and then baking them, heating them, treating them in some way that turns them into what we recognize as food is a really fantastic multi-step look at the complexity that can be in these systems. This also made us think of the smart and connected home. So if we've got refrigerators that are telling us expiration dates, that are tracking the usable shelf life of our food, and saying you should prioritize cooking something sooner, can we utilize that with a system like this? That way you can come home to that food having been prepared based on expiration date. So there's less food wastage, and there's also an immediate serving of what we recognize as food available on return home. There are lots of really broad and large claims being made about the future, again, in that deluge of data. There are some two large directions we're thinking about for the future of additive manufacturing, where things are progressing on a whole. The first is there will be a broadening of material and machine options. I went on Kickstarter 2 weeks ago, and there were over 200 projects asking for funding that were materials or machines for additive manufacturing. The grassroots construction of this is enormous. But what we'll find is those will start rising. Some of them will be successful and they'll take off, some of them will not, and they'll fall by the wayside. In the same way, there used to be 200 car companies in America, there are now 3. Right? You're seeing this already in additive manufacturing companies, Stratasys and 3D Systems. As a small company develops usable, marketable technology, they're getting bought up. So those are coming from lots of small to major large players. The other is that additive manufacturing is going to continue to evolve and hybridize with more traditional manufacturing techniques. We saw this earlier with the fire cast material to say that it's another tool in an arsenal. Injection molding is right for some things, metal sheet stamping is right for other things. Additive manufacturing will have its place as well. We're seeing that in 2 ways. First, with using it as an intermediary step in production, but also we're using it for use in manufacturing lines. If you work in heavy industry or manufacturing, you can see how the scale of those lines, parts break, a gear breaks, a belt breaks, and replacing that piece can be time consuming when you run a 24-hour day, 365 days a year. There isn't time to stop. So the opportunity to print replacement gears or modifications to customize your line and your machinery is really unique. To have that on-site solution in traditional manufacturing for high volume is key. This is also a great point to discuss speed. That's a question that comes up very, very often. when will it be faster? When will it be fast enough to print for fabrication on a mass scale? And the challenge for that is twofold. There are physical limitations. There's limitations to how quickly a nozzle can move with precision. There's limitations to how quickly a plastic will resolidify before you can deposit another layer. It will get faster. It may never get fast enough. But if we think about speed more holistically, we'll realize that there are incredible time savings in certain instances. If I'm producing one bespoke piece of jewelry, the idea of tooling a mold to produce one would be an incredible waste of time. But if I can do a single print, even if it takes 5 hours, that's a savings over tooling a mold. So as we think about the speed and the different ways to interpret this going forward in the future, look at some ways to interpret this in specific business cases. There are 4 broad silos we put this into. Incremental adoption, to improve in small ways to the current product and the current supply chain. To rethink the supply chain, to rethink the product, and then to reinterpret through a completely new business model. Some examples of those. I'm sure everyone has seen the Nike Flyknit. This is produced through a 3D knitting process. And aside from a wonderful marketing campaign and interesting performance attributes that are available because of the structure of the knits and the very specific areas of different tension and elasticity, Nike's created a beautiful shoe. They're still selling shoes, they're still selling them in stores, so this is an incremental change to their product offering. But what's really unique is, again, about speed. It takes a while to knit something with that level of complexity and precision, but they've reduced the parts in their uppers from approximately 35 individual cut and sew parts per sneaker to 2. Right? So the time you're spending in knitting that piece is offset by very high-speed construction, less labor, and more precision in that process. We can also change the way in which the current product is offered. This example is a self-lubricating filament from IGUS. IGUS makes plastic bushings and bearings for everything from cars to industrial lines. And what they've done is they've put their proprietary plastic into a filament format. They've recognized that people are looking for replacement parts to produce on site, or that they want to prototype and customize their own bearings for custom work, proprietary development at individual manufacturing plants. So by offering their product in this format, they're recognizing the need of their consumers to customize and make on site. So in this way, rather than selling them a truckload of bearings for one size, they can be first in mind for custom production and be the first name in moving that development forward and providing a performance plastic with self-lubricating properties. There are also innovations in product and offering new products in new ways. So here you're seeing 2 images of the same component of a tensile bridge. The one on the right is water jet and then hand welded. The one on the left is water jet cut and hand welded. The one on the right is fabricated through a sintering process. Fully metal in both cases. What was unique about the design of this bridge is each one of those components was unique, over 300 of them. So here again, if we think actually about time savings, water jet cutting and then hand welding. So though the welding of these artisans is very precise, it doesn't have a particular aesthetic to it. And also, if you've got one person welding, they're producing one at a time, even if you've got 4 people welding. What's lovely about the additive manufacturing is you've got greater precision. You're able to add in decorative elements that have a precision level beyond what was possible in the original. And you can produce as many as you're able to fit in that powder bed at one time. Right? So as large as that volumetric build space is in any printer, you can print 1, you can print 25. So you can run that machine overnight, and when you come in the morning, have 25 finished. This is also a conversation about the hand of the machine versus the hand of the designer, about bespoke, and can you make bespoke things more efficiently with this type of machinery. And the fourth was the change completely in business model. And this is something that comes up a lot. Will this be the end of manufacturing? Is this the decentralization of industry? In a small scale, in some cases, perhaps. I don't believe we're ever going to stop going to the store to buy a coffee mug. Already we own plenty of coffee mugs, and slip casting is fast and cheap and effective. Also, the type of machinery you'd need to process that at home is price prohibitive. People will buy a maker bot from Home Depot for a few $1,000s, but $60,000 worth of multi-jet modeling is more than most people want to put in their garage. In this instance, a company like Shapeways is a really good example. So they're changing the peer-to-peer model. So there are online places like Etsy where I can buy bespoke handmade products from a peer. What they're doing here is, rather than having a product made and then sold peer-to-peer, someone is designing a 3D model. The idea of that product is being sold, produced by Shapeways, shipped to that person after it's been sold. There's no fabrication until after sale, and then a cut of that sale goes to the original designer. So it's peer-to-peer with an industrial intermediary. What's really interesting about this is the shift. If you think about the 1970s, if you ordered something from a catalog, right? Somebody designed it, they made it, you bought it, you waited 4 to 6 weeks, and then it was delivered. Now we wait 1 to 2 days, maybe 3 days from Amazon. So now what we're doing in this instance is we're designing something, selling it, shipping the digital file, and then making it. So we're designing, selling, and shipping before anything's been fabricated. There's less waste in the system, there's less redundancy. The end of sample sales, perhaps. So if we can change the way in which we deliver products to people and offer them more of what they want when they want it, that's going to be a significant change in the way industry serves product needs. Additive manufacturing as a whole is going to continue to offer better, unexpected solutions to our existing problems. So for medical use, we want precision, we want low volume, and we're not really worried about price point. So it's fit really nicely in there, right? Where we need very specific and bespoke work, there are solutions there as well. So there are many problems that we're contending with, and in a few instances, this is continuing to prove to be the right tool for the job. And as we learn more about how to utilize this tool, how it can serve larger systems that are already established, I think we'll find it's got solutions to a broader range of current problems.
Thank you, Sarah. We're now going to open the floor to questions. As a reminder for our listeners, if you have any questions, please feel free to type them into your questions pane on your screen. We're going to try to answer as many questions as possible in the time we have allotted. Okay, so Sarah, we have one question from a listener about additive 3D printing, meaning 3D printing into another existing material like textiles. Are there examples of that?
So to combine the ability of product laydown onto a different substrate? Most of the things we've seen currently have been freestanding, and different printing techniques like screen printing or casting have been used to add onto surfaces. But given appropriate adhesion, I think that would be the question. There was a collection with Pringle of Scotland where they did a collection of printed components that were then introduced into the sweater through knitting. So rather than printing directly onto the substrate, they printed and then combined through more traditional fabrication techniques. So I think that moment of combination is going to be about how to adhere or bond pieces together more than about which technology would be the correct precursor.
So we have another question for you, Sarah. Do you see the possibility for 3D printed models to be reused and made into recycled filaments?
Absolutely. That's one of the really interesting disruptive technologies right now. If you've worked with a 3D printer, you know that it's not the same as your Keurig. You don't press a button and the coffee comes out, right? There are mistakes and there are skips and there are products that you've fabricated that you've made a mistake or the machine's had an error. And there's some waste in that system. To your point, there are currently machines where you can at home melt and re-extrude your own filament. What's really interesting going forward is that you're seeing through all these different additive manufacturing techniques, there are requirements for the format the material is furnished to the machine in. That is one of the challenging limitations. It's not the machines can't necessarily process it, it's just that it's not being made available yet by a manufacturer. There are currently some machines being developed, specifically one called Sculptify, that will accept pellets. So the majority, if you buy a truck full of pellets from DuPont, any sort of plastic, that's all coming in that pellet or nurdle format. So if we can change our machines to accept the commercially available commodity plastics that are available on the market now, we can really open up a breadth of possibilities.
Sarah, has there been any success in materials other than resin for stereolithography?
Yeah, the challenge with that is that it does need to go, it's light catalyzed polymerization, right? So we're moving from monomers to polymers. I guess the question would be, no, currently they're all polymers, acrylics. If you could combine somehow, so if you think of, in stereolithography, if you could combine in a secondary material that was being held within that polymer matrix, that might be a way to do it. How you ensure that that particulate is dispersed evenly, I think that would be your big challenge.
Are there any databases that you could recommend for our listeners of different 3D printing machines and services?
Yeah, absolutely. So actually, in the back of our own 3D printing report, we do have a list of commercially available machines. Some of those are small, do-it-yourself at home machines, the MakerBot. The RepWrap is actually really interesting. It's a constantly evolving source of design and engineering information that you can build yourself at home. And then there are also the machines from 3D Systems and Stratasys that are an investment piece for a design facility or a manufacturing.
So we just got a great question. Has anyone created a multi-head printer to reduce production time and increase the number of parts that can be produced at the same time?
So there are some multiple head printers. The one I'm thinking of right now is there are two offered by 3D Systems and Stratasys that are multi-jet and polyjet printing. And what they're doing actually, rather than printing, you can print things simultaneously. To your point, that head will have to go to each of the locations of each of the objects. But what's interesting about this is they're holding different curable resins in each of those containers. So rather than extruding or depositing material A, I can get 6 different materials, and also I can combine those. So if I've got 2 different shore hardnesses, I can deposit them at the same time and start making permutations of all those mixtures. So for multiple materials in the same print, yes. For printing multiple things at the same time, from what I've seen, and at the rate this is developing, there may be gaps, but really we're taking one print head and moving to multiple locations to print things simultaneously.
So the next question, and this one's good because we've gotten this a lot from a lot of our listeners, what's the best way for a curious designer to just get started?
For sure. So if you're looking, it depends what you're looking for. If you're in a place to invest in a small desktop 3D printer, those are available in all of the technologies we reviewed today. There are some small scale ones actually for dental offices that are very unique, that work on a scale that could be suitable for a small design studio. If it's not something you want to invest in hardware, I'd recommend pursuing, there are service models. Shapeways is a great one, Red Eye, there are others. There's also 3D hubs. They provide access for people to utilize their neighbors' 3D printers. If you have a 3D printer and you don't happen to be printing anything right now, somebody can send you a digital file and provide that as a localized service model. So I'd look for service models if it's something you want to give a try, see if you're happy with the product that comes out the other end.
Thanks, Sarah. This is another one that we got multiple times. Are the polymers or plastics, would they be considered toxic substances? Are they eco-friendly? Is that something we have to worry about?
Yeah, that's sustainability and ecology is always a difficult and hairy problem because there are many, many attributes. You want to think about where the feedstock is coming from. Do you want bio-based? Or do you want to think about end-of-life, recyclability? Some of the concerns are about processing. On a whole, there aren't really challenges. There have been some concerns about ABS and about the heating up of ABS. If you're in a well-ventilated room, and by well-ventilated I mean, has a window, that's fine. The volume you would be taking in is negligible. Any of the other processes, they're always, challenges to machinery and dangers in heavy machinery, but these are all fully contained systems that without gross misproper use wouldn't be damaging to the user. From an ecological standpoint, you can look to materials like PLA and some of the PHAs that are bio-based, so then you're not using oil feedstock. The challenge with those is if you end up with a lot of scrap at the end of your process, there is no municipal way to dispose of those unless you have industrial composting available to you in your city. If you look at something like a polypropylene, a polyester, something that is recyclable in your curbside blue bin, that's a great option as well if you're worried about end of life. That's why sustainability is a challenge. There's components throughout that life cycle to consider.
So this is an interesting question regarding business models moving forward, and specifically purchasing of CAD files online. Do you have any thoughts on how you see the licensing of the drawings evolving over time? Like, for example, shapeways. Have there been any issues that you've heard of so far?
Yeah, the internet can be a dangerous and scary place. So as we can see, security of information that's available through the internet has limitations and challenges. Files are pirated from major motion pictures. Credit cards are hacked. There's a challenge around security there. But to your point about business models moving forward, currently Shapeways offers a product system. So they're going to upload something that a designer's put at a certain price point, and that's a free market economy. If it's produced, it's paid for, it's shipped. And something else like the Thingiverse, where it's open, anybody can upload something for free, download it for free, modify. There's a lot of freedom of information, and projects like the RepRap are promoting that grassroots space. There are challenges when people, because anytime you've got a large group of people trying something new, there are going to be choices made by those individuals that others might not approve of or might not prefer. Aside from computer security and a lot of feet on the ground for patent or copyright infringement, I think it'll be challenging to enforce.
So this question pertains less to business and it's more of a technical question. Can you print different densities or durometers in a single printed part currently?
Absolutely. Multi-jet modeling and polyjet are both doing that from 3D Systems and Stratasys. It's a very widely done system. It's UV curable. And what they're doing is, that's one of the multi-head printers. So we've got different shore hardnesses of resins, different colors, so we can combine those in layers, depositing different durometers at the same time to get a full spectrum. So say we've got something at a 10, something at a 25, a 50, I can get to a 30 by a certain ratio of combination.
So one area we've heard a lot about, and there's been a ton of experimentation, has been with body parts. Can you comment on its future?
Absolutely. What's been really fascinating about the medical industry, which I think is showing wonderful application of this technology, medicine and healthcare currently has the right environment to help this grow. Low volumes, customization is key, and price point isn't so much of a challenge. People are willing to sacrifice finance for their health, and the benefits to customization for healing time and care are huge. So body parts are interesting. They're really undergoing a shift from the rigid and the external to the squishy and the internal. Right? So prosthetics is one of the first things we've seen. There's some companies that they'll scan for example, if someone's lost the lower half of the leg, they'll scan the remaining leg and make an inverse replica of that shape, so you can get an identically structured piece. And some of them are moving into making them beautiful artworks to say, if it's not going to look like the original appendage, let's make it a beautiful art object. And now we're also seeing scaffolding. So bone scaffolding, and hopefully in the future scaffolds for organs. The challenge is that these scaffolds are really about the structure and the shape, because a kidney bean shaped object does not function like a kidney. So we need to combine those scaffolds with cultivated cell growth. We need to grow active kidney cells on that structure and incorporate them into the bodily system. That's probably, we want to say, 10 to 20 years out. They're doing a lot of really interesting development work in that space at the university level currently.
So beyond healthcare or the medical industry, what industry do you feel has the most potential when it comes to adopting additive manufacturing techniques?
I think it's about upstream industry, and in that way, all industries. So if you're running a nonwovens line, if you're running a automotive line, and to our point earlier, if a gear breaks or needs replacement, a lot of times what people's proprietary components in manufacturing are is you're going to buy a Stoll knitting machine, you're going to buy a Truchenberg nonwovens line, and then your team is going to disassemble, reassemble, and customize that for your needs. And this is going to offer new opportunities in high volume manufacturing by making the parts that make consumer products.
So one of our listeners mentions that they find limitations to the 3D industry when it comes to using parts that demand strength. Do you see that changing?
Absolutely. So one of the ways that's changing is we're moving into more opportunities for working with metals. A lot of the electron beam melting process, the selective laser sintering we can do, we're getting metal parts with the mechanical strength comparable or improved over that of cast metals. Some of the nylons, I think the challenge will be about using the right tool for the right job. Electron beam melting can give you fully titanium parts with comparable properties. We're using these in spaceships. We're using these in jet fuselage. So if you want to scale up in performance attributes for either finished goods, it's going to be about tuning the system you use and the materials you use, again, to the properties you need. Depending on what level of strength you're talking about, I'd look into metals and direct metal fusing. But you know, it may be served by a well-printed nylon piece. One of the challenges is quality of print. I can use strong materials, but if I haven't done a good print in a well-designed file structure, I won't get those properties out of my material.
So one of our listeners asked, is there any color matching standards currently in place for 3D printing, such as Pantone?
Yeah, for full color prints like you see in inkjet and powder bed, there is a degree of variation in color due to the way the material absorbs color, but actually it's getting a lot better. There's really quality matching. HP recently just got into the printer market, and that will be interesting to see how the quality of color changes there. I think the challenge will be in communicating the variance in color from what's on screen to what's in print. Anybody who's hit print on the document knows that what you see on screen doesn't necessarily match what you see coming out of your printer, and it'll be the same with 3D as opposed to paper printing. I think it'll also be a question of using some secondary processing like we do for quality control in manufacturing. Can we calibrate our screens? Can we calibrate that printer? We'll need to do very close matching to get that. But I think the technology has the capability. We'll just need to calibrate and use it carefully.
Thank you so much, Sarah. That was really great. Unfortunately, that looks like that's all the time we have today for questions. However, please feel free to email us at consulting@materialconnection.com with any questions we were unable to get to, and we'll do our best to get back to you. On behalf of the Material Connection team, I want to thank you all for joining us for today's webinar. For more information on this incredibly innovative industry, check out our exclusive Material Revolution report on additive manufacturing. The report includes expert interviews with key industry leaders, a visual glossary of additive manufacturing processes, a glossary of key additive manufacturing materials, and much more. You can place your order today by visiting our website, www.materialconnection.com. We'll send you an email shortly, including a link to our follow-up survey. We appreciate any and all feedback related to this event. Also, look out for our email alerting you to the on-demand status of today's presentation so that you can review any material you missed or simply want to go over again. Again, thank you for joining us.